Good morning. Good morning, everyone. Uh, Very happy to be back and talking about semiconductors, right? That is the subject we have been talking about, different aspects of it. And today we are going to look at. um so we have seen that how the atoms can affect the property of a device or whatever we are making. But today we are going to look at closely how does let's say a device which we are building can affect the property of the circuit or the functionality which we want to build with that, right? Simple function, how does that is dictated by the property of that device, right? Because that is what we typically known as in the community as the device circuit co uh, design or co-optimization and or the co-interaction, right? So that is the uh, how does they how do they interact, and how does one let's say design better circuits or devices with this kind of understanding. So that brings me first, and we are going to talk about our favorite MOSFET. That is what we have been looking at, right? Um, because it's just it's been the workhorse of the industry, and you see billions of it on chips which you are getting right in any of the computing system. So that means we see that this is the typical um, structure we have been talking about. We know that this is the N MOSFET, which is the N channel. There is a P channel counterpart of this, right? So we know that when we apply a positive gate voltage to this, there's a current flowing from drain to source as a response to it, right? Similarly, the control voltage, if we apply negative here, there's a current from source to drain flowing as a response to it. So that is what is the effectively the idea of this PMOS and NMOS, right? And then when we see, okay, you have been talking about, or we have been talking about this using this MOSFET as a switch, right? That is what the initial thing which we talked about. And as a switch, we saw that we even built a simple NOT gate, right, using this, where we had a switch, which was, so we know that we can give positive, so 0 to positive, let's say like 5 volt. This could be our zero, logic is 0, and this could be 1. And at the output, if we are making a NOT gate, we want 1 or 0, right? That is what the idea is. Now, to get 1 or 0, we had to keep this node floating, right? That was the idea, the drain node. And what was it controlled by? Because it's a current changes when we change from 0 to 5 volt. We dictated that with a resistor which was connected to, let's say, a VDD of 5 volt, for example, right? So that is how you see when you apply 0, right? When VG is 0 to this, we know that the transistor, because VG is, there is no conduction, so that means the current which is flowing from drain to source is going to be very close to 0, right? It is not 0, it is close to 0. And when it is close to 0, we see that the drop across the resistor, let's call it VR, right? So VR is also close to 0. When VR is close to 0, we know the VD is nothing, or VDs, which is our output, right? Um, which is equal to your VDD and the drop across this resistor, right? And if VD, then that means we see that your V out becomes close to 5 volt. So now you have achieved at least one inversion, that you applied 0 volt and you got 5 volt here, right? Similarly, the other case of it would be where when VG is equal to 1 volt, sorry, not 1 volt, 5 volt. 5 volt is the logic one, right? And then we see that there is an IDS which is going to flow. So, right, the finite IDS. And that would mean your VR is going to be whatever is your IDSR. And that means your V out is going to be your VDD minus this IDSR, right? And if this IDS is higher, very high, that means you can see that your V out could be very close to 0 volt, right? Not 0, but close to 0, right? Which in logic terms, it would mean it's a logic 0, right? This was what we saw here was logic 1. So that is how you see now you started with the logic 1 on the gate, but you got logic 0 on the drain, right? With this resistor. So that is what would give you, or we can say it's a very simple case of inverter, which can be also a NOT gate, right? Now you can ask, okay, so then that is very good. That means we are converting from a 1 to 0. But how does my device dictates the operation of the NOT gate, right? That is what the first question one would get. And for that, one needs to closely look at the input output characteristics of this circuit. This is like the whole, always the holy grail in if you are analyzing any circuit, is to look at the input output characteristic, right? We know our input is going here, which is going on the x-axis, and then we plot V out on the y-axis, right? We already know the bounds of it. We know that this is our 0 volt and this is maximum we are applying is 5 volt. Similarly here, there is a 0 volt and there is a 5 volt, right? And we know when we are applying 0 volt, we are very sure that the output which we are getting is very close to 5 volt, right? So that means we already know this point, that that is where we are starting. But now what is happening is we also know that this part, that when 5 volt is there applied, there is a finite current which is very close to 0. So it means there is a some voltage very close to 0, which is not 0, but there is a some difference, right? There, but that is close to 0. So this also, we know this point also. Now what is happening in between, right? And if you were to solve this, you can solve this also knowing how the current changes with the input gate voltage in a transistor. And that's where you use, let's say, any model, or we typically use very simple models for modeling this MOSFETs. Let's say like the square relations you would have seen. So for example, one relation I can write is like we have seen that our current depends on some coefficient Kn, which is WL by times your VGS minus VT into your VDS minus VDS square. Right? So this is one of the current which you see that how does that dictates your regions, right? But this has to be solved along with this circuit equation, which is which we wrote there as V out is equal to your VDD minus IDSR, right? They have to be solved because VGS we know can be V in, right? We can substitute this with V in. But when we put in this equation, the VDS is now output, right? So VDS becomes your output. So then you see that there is a, what do you say? It's a implicit equation, right? Because when you put in this, you see that there is a equation which is function of V out also. It's not like Y equal to MX plus C, right? And that has to be solved. When you take in the V in, all the V out on one side and V in, and then when you see, you solve this, you get a function like this, which decreases, and then it becomes like this, right? So that is the, this we can see this point closely, because we know when does our transistor become on, or when does it start conducting, and we know that this point is our VTH of the transistor. So that we can see now, which is one property which directly depends on device. And then we see the slope is also very much dependent on the coefficients and everything we are putting in inside the transistor, right? So because it is directly coming from that. So now one can see that if, let's say, this point, if let's talk about VTH itself, right? If VTH was very small, then we would be able to see that when this is logic 1, right? When we are saying this is logic 1 and when we are saying this is logic 0, right? So logic 0 would be, let's say, um, logic 1 is quite clear. So let's divide this into two parts, right? So what you are saying is, okay, in this part, whatever is coming is our logic 1, and in this part, whatever is coming is our logic 0. So then you see from this curve itself that the VTH is a very important parameter which defines that for what part you are having this as a 5 volt, right? Here we see for what part you are going to have this as a, and what is in between is the transition, and which is dictated again by the parameters which are defining your current. So for example, Kn, if you see, if we expand this, this is mu and Cox, which we have also talked about the mobility of electrons. Let's say, for example, here, right, this is the electron mobility. So then if we see this is the electron mobility and that is a device property, it is affecting the way your output input output curve looks like, right? So if you had that is why, so this is a very interesting exercise one can do in a, let's say, software like I would suggest like LT Spice, for example. You can just make these simple circuits, and you can choose NMOS model, and where you will see these parameters like mobility, Cox, and the other whatever parameters which are there for the MOSFET. And you can see when you change this parameter, how does this change? And I would also ask you to look at that when you apply, for example, you just don't stop there. You apply to this circuit, for example, a square wave, right? Then you see, okay, how does my V out looks like, right? How does it look like? Because that whatever is the property of that NOT gate which you're getting is very much now dependent on the device property, right? On this curve itself, right? How on this curve you are moving. So ideally we want to go from 0 when we are here, right, at this point, and we want to go to this point. This is what in between this is happening, right? 0 and 5 volt. Similarly here 0 or whatever is the logic 0 and that 1, right? So let me describe in the logic itself. So this is logic 1 and this is logic 0, right? So like that. So that is the thing. Now you see between these 2 points, if it is going, you would see, okay, what is this? Your transistor cannot just magically jump from this point to this point. It has to go through this path, right? And when it goes through this path, of the V in, you see how fast or slow it would respond depends on this path, right? How fast and slow it would respond depends on the path. Because when your V in is increasing here, when we see the V in is increasing, right? Though it is increasing much faster here than what it is happening, which is the property of the square wave. But you see that whenever it is increasing, at every point you are determining the V out, and that is how your V out is dictating. Right? So that is one of the key, which is what we know as the transition region, right? Region can define the characteristic of your gate, right? So that is one of the insight one can get looking at just this NMOS, that a simple transistor which is making this NOT gate is defining the very much the characteristic of how does the output look like, right? Because if you make any changes in the device, you will see this is going to change your output. And that is why I invited you to look at this LT Spice and kind of do this. And if you are interested, we can do and show that how to use LT Spice and do all this kind of thing, because that gives you a freedom to explore now from device to circuits what we want to do. Okay, so with that I think I will close here, but there is obviously more coming in when we go into the field of device. It's just not one, but here there is a very clear way of seeing that how the device parameters, right, which are the device like this, which would directly affect my circuit performance, which is the gate, right? So in gate, when we are talking about, we are talking about how fast it is switching, right? We are talking about, and that is now very much dictated by this transition region, how fast it is switching, right? How fast or how slow is the current decrease or increase which is happening would define in the end that how fast it is going to switch. And it's not just the current, there is always another thing which we would talk about in detail when we see these circuits, that how, what is the property of circuits, which is a subject in digital circuits typically, right? But as of now our focus has been more on understanding the impact of device on a simple circuit like a NOT gate, right? So we can explore, extend this for looking at more analog kind of circuit like amplifiers and something you would have heard. And that is what maybe we would look at in the next video. Okay, so with that, thank you and keep growing, keep learning, everyone, and looking forward to hear more from you. If whatever, anything you feel that you had problem with, you just let us know, and I will try to probably look at it. And you never know, right? So because there are different perspectives or of every concept, so something may click, something may not, and probably then you have to go more into it. And because every learning is not by the person who is explaining can put in your brain, but he can provide you the tools. The way, if you explore by yourself, you will be able to make sense of that concept or that thing, right? So that is what I think as an instructor and educators we try to do, right? And I hope that you will connect and you will ask a lot of questions which I'll be more than happy to answer. Thank you, and bye bye everyone.